Okay, we're looking at the energy involved in heating up a gas. If we assume constant volume V naught and pressure P naught, and P naught might or might not be atmospheric pressure, depends on the situation. If we have that information and also a minimum and maximum temperature, then we can calculate the number of moles easily. And as you should be aware, we're going to use the number of moles when we try to calculate the energy that it takes to heat the gas. Okay, so we have some number of moles, and we're going to run temperature from some minimum to some maximum temperature. Okay, so we're expanding at constant volume, as in the preceding video. We're just going to raise water to the maximum height rather than raising it to the maximum, to half the maximum height, say, or some height between 0 and the maximum height, then allowing the gas to expand to constant pressure to force water out and change the potential energy of the system. Okay, we're just looking at what happens during that first phase, assuming that the first phase is it, that we just raise water to the maximum possible height. So we're assuming, again, that the tube is narrow so that the volume stays constant at V naught. So we're not going to have to worry about just what the maximum height is. And we're not going to have to worry about what temperature, at what temperature the maximum height occurs. It's going to be the maximum temperature. Okay, and we assume Tmax and Tmin are given. So I could maybe write those on the assumptions. Just put them up here to indicate that they're assumed to be known. So anyhow, what do we get? We have expansion at constant volume. So we're going to use the coefficient or the specific heat at constant volume, the molar specific heat at constant volume, which is going to be either 3/2 R or 5/2 R, depending whether we have the monatomic, the first case, or diatomic, the second case. And you should understand where these excuse me, come from. I think maples are blooming or something. Okay. So what's the change in internal energy? Well, the change in internal energy is just the total amount of energy you put into this thing, because only the internal energy is being increased. No work is being done. So all the energy you put into the system goes into increasing the internal energy. And that's just going to give us change in internal energies and CV delta T. Again, all the energy that goes in just goes into increasing the kinetic energy of these randomly colliding molecules, whether monatomic or diatomic. So the work done is 0 because there's no volume change. So that the integral of P dV is 0, since the initial volume equals the final volume. The limits on this integral with respect to volume are going to be the same. You're going to get 0. So the change in internal energy is delta U plus delta W, and that's just your delta U because delta W is 0, and that's going to be NCV delta T plus 0, or just NCV delta T. There was some confusion on this issue. Some people were asking questions, well, what about delta W? And we know that delta U and stuff is involved. Go back to common sense. Okay, nothing is expanding, so nothing is moving. So there's nothing to do work against, okay? And the energy that goes in, again, then, just goes into the internal energy of the system, which is the kinetic energy of your molecules, that's the 3/2 R, or if you have diatomic, the 3/2 R, the translational kinetic energy, plus the 2/2 R that you have to expend in expanding the gas. Okay, you don't have, I'm sorry, the 5/2 R comes from the 2/2 R from the rotational motion, the 2 degrees of rotational freedom. If you didn't have constant volume, if you had constant pressure, you would have another 2/2 R on both of these, as I believe you know. So this is what we get, and the energy that has to go in is just the energy required to increase the internal kinetic energy of the gas. And a quick calculation: if the initial volume is 10 liters and the gas is air, then you do, and you plug your P naught, V naught, and so forth, and we're going to assume atmospheric pressure. I didn't write that down. Maybe I should. So pressure is atmospheric. We get to 0.45 moles, very simply. And CV is going to be 5/2 R, which is about 30 joules per mole Kelvin. If we're going from temperature 300 to 400, which was the situation previously, let's write that down. Tmin is 300 Kelvin. Tmax is 400 Kelvin. Then the delta T is 100 Kelvin, so the delta U is just the number of moles, 0.45 moles, times the specific heat, which is 30 joules per mole Kelvin, times the 100 Kelvin, gives you about 1400 joules of energy.